Good day to you from Chem Help ASAP. In this video, we'll demonstrate a relatively recently discovered chemical reaction that is an example of something called a click reaction. We will discuss the reaction, perform the experiment, isolate the crude product, and characterize the material. Handouts for the lab procedure and NMR spectra are available through links in the video description. Let's begin by talking about an older reaction, the cycloaddition of an azide onto an alkyne to form a 1,2,3-triazole product. This reaction is closely related to the Diels-Alder cycloaddition. It occurs in one step. It often forms a mixture of regioisomers. This reaction is an example of a 1,3-dipolar cycloaddition. The mechanism is at the bottom of the slide. With the azide drawn out completely, you can see that the azide group, while overall neutral, does have formal charges. These formal charges make the azide an example of a 1,3-dipole, hence the reaction name 1,3-dipolar cycloaddition. Some dipolar cycloadditions are quite old. They are often called Fokin cycloadditions from a scientist, Rolf Fokin, who researched them in the 1960s and raised awareness of their general utility. Fokin died recently in 2020, just short of his 100th birthday. Let's fast forward to the type of reaction we will perform today. At first glance, this looks like a classic azide-alkyne cycloaddition to make a 1,2,3-triazole. What is different is the inclusion of a copper catalyst. Note that instead of forming a mixture of products, only one regioisomer is formed. This is a copper-catalyzed version of the reaction. It is not a single-step reaction. The mechanism is much more complex and requires multiple steps. Regardless, the copper-catalyzed version is far faster, can be performed at room temperature, and is normally higher yielding than the non-catalyzed version. This new version is called the Copper-catalyzed azide-alkyne cycloaddition and was discovered independently in 1998 by two groups of scientists, one led by Meldal in Denmark and the other by Sharpless and Fokin in the United States. Sharpless coined the term click reaction to describe how this type of reaction rapidly and efficiently assembles the product. Fantastic. So here is the exact reaction that will be performed in this video. We will start with benzyl azide, which I described making in another video. We will also use phenyl-acetylene. Both of these reagents will be combined as solutions in toluene. Finally, we will add just a tiny amount of a copper 1 salt as the catalyst. This particular copper catalyst is described in the reference at the bottom of the slide. It is not the best catalyst for this reaction, but this particular catalyst is good enough and also very easy to make and store. Okay, let's get started with the experiment. Well, let's begin this reaction by weighing out some samples. Our first sample, in fact the only one that we actually have to weigh out, is this reagent. This is copper bistriphenylphosphine nitrate. This is our catalyst. It's a copper catalyst. Now this is, we really need very little of this material. You can see it's a white crystalline solid. And I'm not going to worry about weighing it too carefully. I really just want to make sure we get, no more than 10 milligrams. The amount we really need is like 6 milligrams. So it's just hard to weigh that precise of amount of material in this manner. And we don't need to be precise. We just need to make sure there's a little bit in there for this reaction to occur. Oh, okay, well, that's only 2 milligrams. That's not too terrible. How about this? That maybe is going to take us up to 3 milligrams. Yep, that says 5. That's going to overshoot it, but that's okay. That is, we have overshot. We have a whopping 7 milligrams. That is just fine. So 7 milligrams, that's our amount of catalyst. We'll end up taking this over to the hood and adding it to the reaction flask once we have all the other reagents present in the reaction. Okay, we are now in the hood, and we are going to start our reaction. In addition to the catalyst that we just weighed out, we're going to put everything into a scintillation vial. This is a 20 milliliter scintillation vial, and I have a stir bar in there. It could, because we will mix it once everything's in. And to this vial, in addition to the catalyst, which will go last, we will add a solution of the azide. This is benzyl azide. It's a 1 molar solution in toluene. And we're going to add some of the alkyne. This is also a 1 molar solution in toluene. So I'm going to add these with a pipetter. And this is a 1,000 microliter pipetter. It goes up to 1,000 microliters, and I have it set for 1,000. So let's go ahead and add our solution of benzyl azide. This will be 1,000 microliters. 1 molar solution in toluene. Squirt that in, blow it out. Good. Okay, that's very close to 1 milliliter of a 1 molar solution, so that's 1 millimole of that toluene solution. I'm sorry, toluene solution with benzyl azide. And now, this cap is on here pretty hard. I need a second hand. Now we'll add our 1 molar solution of phenylacetylene. Work that in. And dispense of that tip. And cap our vial. And now the last thing to add is our catalyst. I have it to the side. This is the reagent that we weighed out just previously. We'll dump it in off the weighing paper. There's not much in there. Put that in. I mean, that's it. 2 milliliters of toluene plus some reagents in our catalyst. We'll start this stirring gently. I'm just going to place this cap on here. Not going to engage the threads. And I'm going to warm it up very gently. So let's say 40 degrees Celsius. Just a little bit of thermal encouragement for this reaction. But this reaction will proceed without any heat, but it's just nice to push it along and make the reaction time a little shorter. So we're going to let this stir, and we'll come back shortly, and we'll see what we've gotten. Well, look at what we have here. This reaction has been going for about an hour. And look, it is thick with precipitate. In fact, the only space you have in there is where the stir bar has smushed away all the solid and allows itself to stir. So we can go ahead and turn off the heat. I think it's safe to say we can turn off the stirring. And this reaction is complete. So now all that's left is we'll need to filter this material and give it a rinse with a little extra toluene, and then we'll see what kind of yield and purity this product is. So what has changed? On the left, I have a sidearm Erlenmeyer flask, a filter flask set up with a Buchner funnel, and I will concede one thing. I really wanted to use this funnel. This is called a Hirsch funnel. I don't think I've shown this in any of the videos. A Hirsch funnel has a really small filter plate on the inside. So when you isolate smaller quantities of material, you often use smaller glassware. So you don't spread your material all over your large piece of glassware and therefore lose a lot of yield. So the Hirsch funnel is great because it's just like a Buchner funnel, except for he has these slanted sides, and you get this smaller area where all the solid collects. Unfortunately, I can't find any filter papers that fit this thing, so I am using the old reliable Buchner funnel with its straight sides. That's just fine, but I just want to make the point that when you work on smaller and smaller amounts of material, sometimes you change your glassware, so you minimize your loss of material during transfers. But we'll be fine. We'll still get an okay yield in this reaction. So we have the filtration set up on the right, or it's on the left actually. We have our stir plate, and this is our material. This doesn't look like it has a lot of ice. In fact, it doesn't, but that was an ice bath. So we have our solution cooled. So if there's any any product dissolved in that toluene, it's had a chance to precipitate as well as it can in ice. And then I have some cold toluene over here because I'll need some toluene to do some rinsing of this final product once we filter it. So let's go ahead and set up the filtration. I'm going to turn on vacuum. And as always, we seat the filter paper. Now, the solution in this reaction is mostly toluene. So I'm going to use toluene to seat the filter paper. Seat the filter paper with whatever solvent you're using in the filter. So don't just, oh, I'll seat it with water. No, you need to match your solution. Now, tell you what, I'm going to take a quick, no, I'm okay. Whoops. So this is kind of solidified in here. So I'm going to use this micro spatula to break it up. You can see there's still a lot of liquid, but it sort of gets trapped in the solid. So I just want to make sure this is nice and loose and flowing. I don't want to do this too long because I don't want this to get too warm because we put it on ice to cool it down so we get everything to precipitate. But, you know, don't fret too much. You can only work so quickly. Just make sure you get the job done. So that's nice and suspended. Let's go ahead and pour that in. I'm going to pour that right in the middle of the filter paper. That was very thick with solid. You can see there's still some solid in here. So I'm going to use a little toluene, cold toluene, to rinse this down. Now I'm trying to rinse it, not dissolve it. So again, we use cold toluene and we try to work quickly and give a little rinse. And tell you what, let's do that one more time. Then, once we're done, swirl it quickly. Great. I think we're done with that. Our reaction vial, our scintillation vial. And now I'll just squirt a little clean toluene in there. Fantastic. So everything's rinsed. Let's see if we can take a look in there. We've got filter paper. We have solid collected in the middle of the filter paper. So now what's left is to let that air dry, and then we'll collect the solid and see what kind of yield we got as a crude recovery. Well, the product has air dried. Here it is on a piece of weighing paper. That's, the mass that I got was 171 milligrams. You can, I don't know if that shows up on camera. That is, I wouldn't call that white, but that's just slightly off-white solid. Like I said, I got 171 milligrams of the product after drying. That is actually, here is not the full product. I've taken some out for an NMR and a melting point and a TLC, but not very much. So that looks good. So now I already know what everything looks like, but the characterization do look good. And now we'll go through the characterization data, and we will also perform a percent yield calculation. Let's start the characterization with the TLC and melting point of the product. The image of the TLC plate of this product is shown to the left. You can see that this product is UV active, and there is just one spot on the plate. Looks beautiful. The mobile phase for this TLC plate was 50% ethyl acetate and 50% hexane, and the RF of that spot is approximately 0.39. The TLC looks clean. So what does the melting range tell us? Well, this product had a melting range of 130.0 to 130.5 degrees Celsius. The literature value for this product, taken from the reference that described the copper catalyst, is 126 to 130 degrees Celsius. So our melting point is in good agreement with the literature and occurs over a very narrow range. Also a sign of product purity. Wonderful. Here is the full NMR spectrum. This spectrum was attained on a magnet with a field strength of 400 megahertz in a solvent of deuterated DMSO. These upfield peaks are from our solvent. There's water. There is DMSO. Let's expand the region of the spectrum that only shows our product signals. Much better. If you count all the hydrogens in the molecule, we have 13 hydrogens total. When we look at the integration values, we have 2, about 8, 2, and 1 hydrogen. That is a total of 13 hydrogens. Perfect. All of our expected hydrogens seem to be present. The most upfield signal is close to 5.6 ppm, a 2-hydrogen singlet. That would be this CH2 group with no neighboring hydrogens. All the other hydrogens are on aromatic rings. Let's now move to the most downfield signal, this 1-hydrogen singlet at about 8.6 ppm. This lonely signal is the single hydrogen on the triazole ring. Note that triazoles are extremely polarized rings, and the polarization of the ring helps us explain why this signal is so de-shielded and has a chemical shift of nearly 9 ppm. That leaves us this 2-hydrogen doublet and the big lump of 8 hydrogens. Which of the remaining hydrogens are in a sufficiently different environment to have a different chemical shift from the others? It's likely this pair of hydrogens. They are conjugated with and closest to the polarized triazole ring. The remaining 8 hydrogens all have a very similar environment and show up on top of each other. This lump does contain individual signals, doublets and triplets, but we can't distinguish them here. We'll call this an 8-hydrogen multiplet. So this spectrum is consistent with our product. Furthermore, the baseline is beautiful, very clean. Collectively, all our characterization data indicate a very pure product. Keep in mind that this is technically a crude product, since we have not purified it. Still, it is a crude product that is quite clean. This product does not need to be formally purified. Let's determine our yield. For the starting azide, we used 1,000 microliters, 1 milliliter, of a 1 molar solution. Molarity, moles per liter, is also millimoles per milliliter. So 1 milliliter times 1 millimole per milliliter gives us 1 millimole of the azide. We use the same amount of the alkyne, 1 milliliter times 1 millimole per milliliter, or 1 millimole of the alkyne. These react in a 1-to-1 ratio in the reaction. Each reagent is present in the same amount. Each is equally limiting. So our theoretical yield is 1 millimole. Let's go to our product. We isolated 171 milligrams of clean crude material. The molecular weight is 235 grams per mole. When we do the calculation, we find we obtained 0.03 millimoles of product as our actual yield. Take actual divided by theoretical times 100, and this reaction provided a 73% yield. Nice. I want to make one comment about the yield. Note that we didn't do any math around the catalyst. That's because catalysts are not included in the yield calculations. The amount of catalyst can, however, affect how quickly the reaction takes place. The procedure calls for 1 mole percent of catalyst. That means you need 1% of the number of moles of the limiting reagent. We used 1 millimole of our limiting reagent, so we should have used 1% of 1 millimoles. That's 0.01 millimole of the catalyst. Well, we used 7 milligrams of the catalyst. The catalyst has a molecular weight of 650 grams per mole. Therefore, we used about 0.011 millimole of the catalyst, very close to our desired 1 mole percent. I hope you enjoyed seeing this example of a click reaction. Remember that procedure handouts and copies of the NMR spectra are linked through the video description. Please subscribe, like, or leave a comment. Take care.